So at the end of our last class, we developed the algebra of permutations by discovering the three relations that make up what's called the Coxeter presentation of the permutation group. And all of that is a big fancy mathematical mouthful to just kind of say, how do the adjacent transpositions, the operations that take two adjacent positions in a word, for example, and interchange those adjacent positions, how do those interact with one another? And there were three rules that we came up with, three principles that we can use. We can think of them like simplification rules, if you like, for any word that we write that uses the generators of the permutation group as its letters. So for example, this anagram, which is a trivial anagram, it takes the word bears and it turns it into the word bears, but my Braid-a-Gram for this anagram has two crossings in it, right? This string over here crosses over the E string and then immediately crosses back over. And so the Braid-a-Gram is not trivial looking, but the permutation is definitely a trivial permutation because ultimately none of the letters are actually moving. And what you said was that this is a reflection of the fact that every one of these adjacent transpositions, if we do it twice in immediate succession, it cancels itself out, right? So sigma n squared is equal to the identity, because if I just trade two adjacent positions and then I trade those same positions back again, I've just gotten back to where I started. So that encoded this first relationship in the list for the Coxeter presentation. Every one of these adjacent transpositions, sigma I, if we do it twice in rapid succession, what we get is the trivial permutation, which we call epsilon. And this is true for all of the generators, from the first one all the way up to the last one, which is the n minus first, right? So that was the first thing that you discovered in that activity. The second was by taking this ogre to goer anagram and looking at it in two different ways, we sort of figure out that it doesn't really matter to the permutation whether we trade the first and second positions before we trade the second and third, or third and fourth positions rather, whether the O and the G switch before the R and the E, or whether it's the other way around, whether the R and the E trade places first and the O and the G trade places second. We get the same result. Again, two different looking Braid-a-Grams, but two identical permutations. And you sort of figured out that it doesn't matter which order we do a successive pair of adjacent transpositions, as long as those transpositions are not competing over the same strand. And in order for that to be true, we need for the M and the N, the index of those transpositions, to be at least two positions apart. That way they're not grappling over the same strand, they're just kind of doing their own thing to their own pairs of letters, and so it doesn't matter which one happens first and which one happens second. The result is always the same. That gives us the second relation in our Coxeter presentation, which says that the composition of sigma I with sigma j is the same as the composition of sigma j with sigma I, as long as I and j are separated by at least 2. So that's what the work that this little inequality over here is doing. So that's the second relation. It's really a whole family of relations, right? One for each pair of I and j between 1 and n minus 1 that are at least 2 positions away from each other. And so that gives us a lot of these generators that commute with one another. Remember, the commutative property says it doesn't matter what order I place two elements, and a lot of the generators do commute with one another. Unfortunately, if two transpositions are sharing a common strand, that no longer happens. And that was what happens with the third one of these relations, where you find out that, for example, to make position 1 and position 3 trade places, so for the T and the N in the word tones to trade places into the word notes, there are two different ways that that can happen that give us different Braid-a-Grams but the same result. The first way trades the first pair of positions first and then the second and third position, and then trades the first and the second again, so 1, 2, 2, 3, 1, 2, or in our sigma notation, sigma 1, sigma 2, sigma 1. But the very same thing happens if we reverse the order and do sigma 2 first, then sigma 1, then sigma 2. And so we get this interesting relationship that says sigma n plus 1 sigma n is the same as sigma n minus 1, or n plus 1 sigma n. Sigma n minus 1, sorry, sigma n. Or how I write it here, sigma I plus 1 sigma I is equal to sigma I plus 1 sigma I plus 1. So if I have two transpositions that are right next to one another, and so they're going to be sharing one of the strands, one of the positions when they do their work, then this is how they interact with one another. This is called the braid relation, or the skein relation sometimes, for permutations. And so what this does for us is it actually verifies that those adjacent transpositions that are right next to one another and sharing a strand don't actually commute with one another, but they do interact with one another in this very specific way. For example, sigma 4, sigma 5, sigma 4, we can replace that with sigma 5, sigma 4, sigma 5. And so the Coxeter presentation theorem tells us that this set of rules is sufficient for describing the entire set of all permutations that we can do for n strands. Any word that I can spell out using the alphabet of these adjacent transpositions and using the simplification rules that are given by these three properties up here describes a permutation of n symbols, and every permutation of n symbols can be described by such a word. And the process of proving that implication is just, hey, draw a Braid-a-Gram. If you can draw a Braid-a-Gram, then you can figure out how any permutation can be expressed as a composition of these adjacent permutations. So that's where we left off permutation-wise. That's kind of where we end the story of permutations. And then we try to make things knotty, K-N-O-T-T-Y, by taking our Braid-a-Grams and deciding, well, if I want these things to be something I can physically see and touch, then I need at each one of the crossings on this diagram to specify which one of the curves is passing over which one, or which one is passing under which one. I need to give all of my crossings an orientation in order to turn this into something we can physically realize. And when we do that, we turn a Braid-a-Gram into what's called a braid. And the first examples of braids that you worked with were just, I asked you to take those same Braid-a-Grams from the previous problem and just turn them into positive braids. Positive braids mean that all the crossings have the orientation where the northwest to southeast strand is passing over the northeast to southwest strand. And so here's what happens when we make all of those Braid-a-Grams that we did in the previous example into positive braids. And the question that I asked for you, this was the $64,000 question, is, are all of those braids still the same? Do we still see the same relationships between these positive braids that we saw between the Braid-a-Grams and the permutations in the previous exercise? So for example, is this braid that turns bears into bears, at the level of permutations, this was supposed to be a trivial permutation. My question is it a trivial braid? Similarly over here, the ogre to goer, I have two different braids representing that, two different positive braids representing that action. Are they the same positive braid as one another? And thirdly, we have these two different ways of representing the tones to notes anagram as a positive braid. Are these two positive braids the same as one another? So what I want to do is give you a quick 5 minutes to get your head back into this exercise with your teams and decide on the answer to those three questions. Which ones of these positive braids works exactly the same as the corresponding Braid-a-Grams and permutations did, and which ones of them might work differently now that our crossings have orientations? The first thing that you decided, your team, was that this bears to bears, even though it used to be a trivial permutation when we only cared about Braid-a-Grams and permutations, at the level of braids, it looks like there's something going on here that's not trivial with that braid. The two strands, the B and the E strands, are being twisted together with one another in a way that's not really possible to untwist. We can't really say that there's nothing going on there. So just to kind of think about why that might be for a second, just imagine that I sort of grab a hold of the word bears on top and grab a hold of the word bears on the bottom, and I try to like tug on the strands or like, you know, sort of move it around in space in such a way as to try and make those strands there untangle. And I can't do it, right? The only way to untangle those strands would be to either physically kind of take the B and the E and like untwist them, or we might have to cut something somewhere, or, you know, we have to do something sort of traumatic to this braid in order to get it to not be a tangled up braid anymore and just be the trivial braid, which just joins bears to bears without any crossings in between. So I would agree with that suspicion, right? That this does not seem to be a trivial braid anymore. Whereas these two braids that turn ogre into goer, it looks like all we have to do to turn one of these into the other is just kind of put our hands on those crossings and just kind of slide them north and south, right, to trade places. And that doesn't seem traumatic, right? I don't have to do anything too awful to my braid in order to make that happen. I can kind of smoothly change one of these braids into the other without forcing any strand to kind of physically pass through any other strand or something like that. So it looks like that same commutation that happened with two permutations, two transpositions that didn't share a strand because they were two positions apart or more, that commutation still works. And to me, I think one of the most exciting is this third one, the interchange of the first and third positions that turns me from tones into notes. That these two braids, when I look at them on the page, they look fairly different from one another. But both of your teams ultimately talked yourself into a position of saying, actually, these two braids are the same. So what is your argument for that? how could we tell that these two braids that we're looking at really represent the same thing? Here is a visualization of that tones to notes braid-a-gram, done where it's again the N and O crossing happens first, and then after that the next crossing that happens is being drawn over here on the left, because it really is a crossing of the first and the second strands, and then the third crossing that happens back over here again. And so from this diagram, we can see that all three of the crossings are indeed still positive crossings, right? They're northwest to southeast over northeast to southwest, right? So each one of these is a positive crossing, and the T and the N are trading places, but the O, notice what we did here to kind of clarify the crossings, is the O string, instead of just drawing it directly vertically down, we made it trade places with the third string, and then trade places again before it reached its destination. So this just makes it a little bit easier to see. All we've done relative to your drawing is just taken this vertical O string and just kind of, in this diagram, just kind of pulled it over a little bit to expose how the crossings are happening. So actually, I would say that all the crossings that are happening here are indeed positive crossings. So that kind of takes your potential argument away for why these might not be the same braids. But coming back to team 2, I'm interested in the question, how did you answer this question in the affirmative? So how can you tell that these are in fact the same braid? So we can make an argument that all we're really doing between these two diagrams is taking one of the strands, like that T strand, because it's kind of laying on top of the other two strands, and you're just kind of moving it from one side of the NO crossing over to the other. So here is a sort of physical copy of that, right? I've kind of made this braid with the red wire here. This is the O wire. It's underneath everything. The yellow wire here is my O that does nothing. It's kind of in the middle. And then my T wire is the black one over here. So this is the diagram that this group has written on the right. And all I have to do to turn it into the diagram that was on the left is just take this black wire that was above everything and just kind of move it over to the other side like that. One of the disadvantages of using wire is that the wire is kind of stiff. And so it's kind of, it's not being particularly great. But you can convince yourself that this diagram is in fact the diagram that we have on the left here. All I had to do to turn one of these braids into the other was just sort of smoothly reposition the strands without cutting, without untwisting. All of my endpoints are still in the same order. You could imagine if I could just nail those to the table, I could still just grab this black wire and kind of move it to the other side like that. So these two braids are the same because there is a way for me to reposition them inside of space without passing through one another, without cutting anything, without detaching the endpoints, and so forth. That kind of move we're going to talk a lot about today is called an isotopy. An isotopy is just a fancy way of saying smoothly deform something around inside of space without self-intersecting itself anymore, without creating any new kinks or bends or anything like that, just sort of smoothly move parts of it around inside 3 dimensions. And when I smoothly move things around in 3 dimensions, very often the picture that I'm seeing in 2 dimensions can change as a result of that process. And that is where the majority of our challenge in studying knot-like objects is going to come from. Because if we have a physical model of a knot in front of us, it's very easy to kind of understand what knot it is if we can get our hands on it. But once we have to draw a diagram on a page, now we're forced with reckoning with this representational question. That is what I'm seeing here the only way that I can see this particular braid? Or are there other ways that I could see it? And the answer is usually yes, right? Which is a bummer in one sense, but in another sense, it gives us a lot of flexibility. If this particular sort of picture, if this diagram is not my favorite way to understand this braid, if it's easier for me, I can use this diagram instead, right? Or in the ogre to goer example, if it's easier for me to imagine the R and the E trading places first instead of the G and the O, I can do that because the braids are the same. There is an isotopy from one of them to the other. All I do is smoothly sort of move the crossings up and down. It's not actually changing the actual sort of nature of the braid itself, like what braid is it? It's just changing how we're visualizing that braid in a diagram. We've just, I hope, sort of convinced ourselves that the way that the braid generators work for positive braids, so all of these braids S1 and up through Sn-1 are just the positive braids of the ith strand with the I plus first strand. They interact with one another according to the same commutation relation, right? If they're at least 2 strands apart, then they commute with one another. We can do one of them first and the other one second, or vice versa, and get the same braid up to isotopy. And that also this skein relation, that the I composed with the I plus first composed with the ith is the same as the I plus first composed with the ith composed with the I plus first. That those two relations are still satisfied. But the one relation that was no longer satisfied from permutations was that we no longer got to say that the individual generators undid themselves. In fact, let's go back to a physical model on the table once again. Here we go. So this is what, let's suppose that I have a third strand over here that's not doing anything. So this would be a picture of the braid that we would call S1. So I have done a transposition, a positive braiding of the first with the second position, and that gives me this crossing. If I do that again, and do it with one hand, so now I have what we would call S1, S1, or S1 squared, right? I've done that positive crossing here twice. And it's returned all of my positions back to their original position. So at the level of permutations, we can't see any difference between the beginning and the end. But the braids are different because however hard I try, if I grab these ends and just try moving these strings, you know, with respect to one another, I'm never going to be able to untangle that tangle. The only way to untangle this tangle would be to somehow either cut these strands or, you know, take apart the endpoints and do something traumatic like this, right, to undo them. And that would not be an isotopy because my endpoints are moving at that point. So we no longer have that first relationship that we had in permutations, that everything undoes itself. Instead, with the braid groups, what we have to do is sort of ask ourselves, is it ever really possible to undo a single braid twist with more positive braid twists? Let me pose that question to you all, and that will be where we kind of wrap up this introduction. We can convince ourselves that there is no way using just positive twists for us to undo a positive twist in a braid. The only way to undo a positive twist would be to add a negative twist. Let me try and do that with one hand here. I would have to add a negative twist after it. And so I would get something that looks like this, right? I have a positive twist coming first, and then in order to undo it, I would need a negative twist that follows it, right? And in this case, now I can do an isotopy. In fact, I can just move my camera phone maybe to do an isotopy that now shows me this is actually just a trivial braid, right? When I look at it from this angle, it's got those two crossings, a positive one followed by a negative one. But really, if I just look at it from a different angle, I can tell it's really just a trivial braid in disguise. Right? It's not enough for us to just have positive twists to create an algebraic structure, which is a group for our braids. In order to have the inverse property, in order to be able to undo a positive twist, we also need to have negative twists available to us. Right? And so in addition to the braid generators S1 up through Sn minus 1, we also have their inverses. These create the negative crossings. It's a negative twist of the first strand with the second strand with the third, and so on and so forth. So we have to sort of manually add in both those generators and also their inverses. But once we do that, we get a structure called the braid group, which actually is a group. The operation of sort of following braid twist by other braid twists is an associative operation. It has an identity braid, which is, again, just the braid that does no crossings at all. It just connects the top to the bottom with no crossings or twists. And it has the invertibility property because we've sort of explicitly put in all of the inverses of our braid generators. And so it gives us a really nice algebraic structure that is almost permutations, but it's a lot more souped up than permutations were.